this module, we will introduce a new type of analysis called frequency response analysis. So far in this course, the type of analysis that we've been doing is what is termed as time response analysis. We've been finding the output of a system as a function of time. There's another type of analysis called frequency response analysis that we'll introduce in this module, which is very useful for designing systems in general and control systems in particular. Okay. So just to review, we've learned how to determine the time response of a linear system, or the output of a system, as a function of time in response to arbitrary inputs and arbitrary initial conditions. In other words, we can solve differential equations, or given a transfer function and an input, you can find the output. We've also studied the character of certain standard systems to certain standard inputs. In particular, we've memorized the step response of a canonical first-order system and the step response of a canonical second-order system. We've then used algebra and root locus approaches to place the dominant closed-loop poles to give us the desired time response. And by that I mean a time response or a step response that has a certain time constant or overshoot or peak time or whatever. The advantage of a pole placement approach is that we can affect the time response or the output of the system as a function of time directly, and this is ultimately what we're trying to achieve. And when we have canonical systems, this process is fairly easy. For a first order system or a canonical second order system, we have precise algebraic relationships that match the form of the system to the character of its step response. The challenge, however, is when we have non-canonical systems, when we have a higher order system where we don't have one or two poles that dominate, where we have 3 or 4 poles that contribute to the response, or if we have zeros. Then these relationships, these canonical relationships, don't hold, and it's difficult to determine the exact effect of the higher order poles, the exact effect of the zeros. Furthermore, we've sort of been designing our system to achieve a certain sort of character of step response. But if we want to understand how the system responds to different types of inputs, sometimes the step response can be limited in what it tells us. And so it turns out that a frequency response approach to analysis and design can help to overcome some of these limitations of a pole placement approach. So the idea of frequency response is that we input sine waves of different frequencies into a system and look at the system's output in steady state. So instead of looking at how the response of the system changes as a function of time, we will look at how the response of the system changes for inputs of different frequencies. So how does the behavior change as a function of frequency? So it turns out if our system is linear and stable, a sinusoidal input will generate an output that is also sinusoidal and of the same frequency in steady state. And this should make sense if we can think back to what we learned at the beginning of the class. In general, a system's response has sort of a homogeneous part and a particular part. Or you can think of it as a system has sort of a part due to the forcing input, and then it has a part due to the sort of the natural response of the system. And in general, the particular solution will have the same form as the forcing input. So since we're forcing the system with a sinusoidal input of a particular frequency, we would expect the particular solution to also be a sinusoid of the same frequency. So for example, if this is our system G of S, and we feed it some sinusoidal input with frequency omega and amplitude R, then the output may look something like this. And so in general what we have is we have some transient portion that's due to the natural response of the system, which is typically a decaying exponential or a decaying sinusoid. So you can imagine, something like this. The exponential determined by the poles of the transfer function of the system, and then some sinusoidal part, that's due to the imaginary part of the pole, and conceivably some phase shift. So this transient part, the natural part of the system, will die out as time goes to infinity. So this decaying sinusoid will approach zero because it's stable, or as long as it's stable. And that leaves this part, which is the particular solution in steady state, and it has the same form as the forcing input. So here we had a sinusoid of frequency omega, so here we also have a sinusoid of frequency omega. The only difference is that the output may be scaled, so it may have a different amplitude and it may be shifted in time. So for example, if at some instant of time the input is at 0, at that same instant of time the output might be at the peak of the oscillation. And so based on looking at the frequency response of a system, there are two primary quantities of interest. So, in general, what we're doing is we have our system, we're feeding sinusoidal inputs of some frequency, and we're looking at what the system behavior is like in steady state. So it's also a sinusoid of the same frequency, but it could be scaled and it could be shifted. And so the two quantities we're interested in are the scaling and the phase shift. These two quantities have implications in lots of different applications. So one way that we can arrive at these quantities is just by brute force. We can solve the system's equations for different sinusoidal inputs, or we could do an experiment on a physical system where we feed it different sinusoidal inputs and observe the output. It turns out we can also calculate this scaling and this phase shift from the transfer function. So in particular, if our transfer function is g of s, we can calculate the scaling by calculating the magnitude of our transfer function at s equals j omega. So for example, this is our transfer function. If we substitute for s, this quantity s equals j omega, then our transfer function is in essence a complex number. And we can find the magnitude of that complex number, and that will tell us the scaling. And so you can sort of imagine, we have some complex number with some real part and some imaginary part, then the magnitude is simply the Pythagorean theorem. You can simply take the square of the real part and add it to the square of the imaginary part and take the square root to get the magnitude, to get the hypotenuse. And this fact isn't maybe obvious, but they go through sort of an explanation in the book. At this point you can just sort of take it as face value. But this gets back to sort of what we've said it a couple times in the course, how we can interpret S as a frequency. The Laplace variable S can be interpreted as a frequency. We can also calculate the phase shift from the transfer function, where we calculate it as the angle of that complex number when S is equal to j omega. And so in this case, that's the angle. So the angle from the positive real axis to the radius from the origin to the particular complex number, and you could calculate that using inverse tangent, opposite over adjacent, the imaginary part over the real part. And having an understanding of these two quantities, scaling and phase shift, has a lot of implications for designing controllers and designing other things, filters, amplifiers, choosing sensors, designing car suspensions and drive lines and things like that. And on the next slide I'll try and give a little bit of intuition. So for a particular type of system and a particular frequency of input, we can get different scalings in the output. The output could be attenuated, it could have a smaller amplitude, or the output could have a larger amplitude. And this attenuation and amplification can both be good and bad depending on the particular situation. So attenuation may be desired if we're trying to decrease the effect of undesirable inputs like noise, like disturbances. So if we're trying to design a filter, we may want our filter to attenuate some frequency, the frequency of the noise. We want the noise to come in and to be decreased on the output. Or if we're designing a control system, we may want our system to not react to certain disturbances. So if we have some disturbance coming into our control system, we don't want the output of the system to react to that disturbance. On the other hand, attenuation may be undesired. For example, let's say that we're commanding an input. So we have a cruise control, or we have a steer-by-wire system where the driver is turning the steering wheel in sort of an oscillatory fashion. He's turning the steering wheel quickly. Well, he wants the car to actually react to that input. He doesn't want the steering of the car to attenuate his steering command. Looking at attenuation can also be helpful for designing mechanical systems, for example, car suspension. So with a car suspension, if the input is the motion of the road and the output is the motion of the car body, we want to attenuate bumps in the road. Similarly, amplification can be desirable or undesirable, and something that we'll see later on is that amplification can actually destabilize a system, and some intuition for that could be, in essence, you've excited a resonance of the system, so the output grows unbounded, and that's obviously undesirable. Information about phase lag is also important, because in essence a large amount of phase lag means that information into the system is being delayed. So you're trying to sort of perform your control on the basis of old information, and it turns out that this can hurt performance and can also cause the system to go unstable. These ideas may have a little bit of intuition, but we'll try and show it sort of more rigorously why this is true later on. So these two important concepts that we're interested in from a system's frequency response, the scaling and the phase shift, can be represented in different ways. So one way is called the Bode diagram, and it represents these two quantities in different graphs, in their own graphs. So one graph represents the magnitude or the scaling, the ratio of the amplitude of the output as compared to the amplitude of the input versus frequency. So how does that scaling change as the frequency of the input changes? And then it represents phase in a second plot, where phase is also plotted versus frequency of the input. An alternative way to represent this information is with the Nyquist plot, where magnitude is plotted versus phase, so in a single plot. And the Nyquist plot does this using a polar plot form, whereas a Nichols chart also plots magnitude versus phase, but it does it as a rectangular plot. So phase is the horizontal axis and magnitude or scaling is the vertical axis. In this class, we will focus on the Bode diagram.